And with that, I just want to welcome our other co-hosts that are on the call today. Like I said, I'm Melissa Whithelm with the Purdue Climate Change Research Center. We have Hans Schmitz with Purdue Extension. We have Jeff Dukes with the Purdue Climate Change Research Center. We have Austin Pearson, who's also with Purdue Extension. And then we have the one you're here to see today. That's Dr. Beth Hall. She is our Indiana State Climatologist. She joined us about a year ago, maybe around that time. And we are really grateful to have her here with us today. So I'll go ahead and turn it over to you, Beth. And thanks everyone for joining.
Well, hello everyone. As Melissa said, this webinar today will focus on historical observations of variables like temperature, precipitation, and carbon dioxide in order to better understand our past changing climates, the variability from year to year of the components of our climate system, any rates of change, and then any recent trends Indiana has experienced within the past 125 years. Before we can talk about recent historical changes in our climate, it's important to be able to put any changes we might be seeing today into historical perspective. For example, how unprecedented is our current climate changes? Are these changes happening at a rate common to what has happened on Earth over its history? And is this all just part of a natural cycle? The instruments that we use today have not been around for very long. When we think of the weather and climate in terms of temperature and precipitation, we can see that instruments such as rain gauges and thermometers were introduced just within the last few hundred years. Weather radar, that is now so commonplace we often look at the most up-to-date images on our smartphones, was introduced after World War II. It wasn't until the mid-1950s that direct measurements of carbon dioxide were recorded in places like Mauna Loa, Hawaii, and eventually showed us the now famous Keeling curve. Even satellites that really started teaching us things about our atmosphere, such as the extent of cloud cover, water vapor, and global heat signatures, didn't come until the 1960s. So how do we know what climate was like thousands, hundreds of thousands, if not millions of years ago? How do we know if this is the warmest our climate has ever been, if climate change is a natural cycle, or if our current concentration of carbon dioxide is unprecedented? We use what's called proxy data, which is data used in place of actual observations that we're seeking. There are lots of examples of proxy data available to us, such as tree rings, whose annual ring spacing can provide an indication of particularly dry or wet periods, hot or cold periods. Ice core data that has stored particulates, such as from volcanic eruptions and atmospheric gases, such as carbon dioxide, for hundreds of thousands of years to nearly 1 million years back in time, to one of my favorite and possibly more disgusting examples, rat middens, and this is spelled with a D as in dog, as opposed to T as in Tom, where pack rat communities who've lived in the same location for tens of thousands of years have managed to accumulate incredible depths of their own stratified excrement. Here's a picture showing the massive size of one of their accumulated excrement mounds. Scientists can core this material in order to date the changing vegetation sources of their diet over time, to better understand the climate that allowed that food to exist. From a variety of proxy data sources as those, and other scientific discoveries, we've realized several key natural influencers of climate change on Earth. Probably the most predictable and long-term impacting natural influence on climate change are the 3 orbital pattern oscillations as shown in this graphic. Note the time series curves that are shown beneath each pattern. These curves represent the up and down amounts of solar radiation that Earth receives due to these orbital changes, along with their frequency of change. Most importantly, note that these changes from one extreme to the next is in thousands of years, actually tens of thousands of years. These patterns represent how the Earth's orbit around the sun varies from being almost circular to quite elliptical. That's called eccentricity. The tilt of the Earth relative to the orbital plane between the Earth and the sun varies, causing our seasons to be more or less extreme than they are today, and this is called obliquity. And finally, the wobbling, if you will, of Earth, which is where today the North Pole points to the North Star, but this doesn't always happen. It actually rotates and points to other stars within our galaxy. These pattern cycles range from as little as 26,000 years to as much as 100,000 years. When the peaks of these patterns coincide, the climate change impact can be quite noticeable and can help explain long-term climate events such as ice ages. The important thing to realize with this is that while all three of these orbital patterns can have a strong impact on our climate and definitely evidence that our climate has always been changing, it's the rate of change, and it's extraordinarily slow when it comes to these orbital patterns. In the previous webinar of this series, called Getting Back to the Basics of Climate Change, things such as energy from the sun, energy emitted by the sun or by the Earth, particles and surfaces that reflect solar energy back to space, and gases that like to absorb and re-emit Earth's radiated energy were discussed. So what is the role of volcanoes in all of this? I apologize for how busy this graphic is, but I really wanted to show something that would help illuminate the role volcanic eruptions have played in Earth's history. Note that this timeline only goes back to about 2500 BC. Interestingly, there were times when volcanic eruptions seemed to be linked to warmer periods, and other times when volcanic eruptions were linked to cooler periods. So how can this be? There are several different types of volcanic eruptions, and some of them spew out a lot of gases, while others might spew out a lot of particulates. When they erupt, the force of the eruption can send these particles way up in the atmosphere, above where the jet stream is and where large commercial jets fly, above even the tops of the tallest thunderstorm clouds. In this upper atmosphere, the air is incredibly stable, and particles and gases can stay suspended for a long time, such as years or even decades. If a volcanic eruption is strong enough to send particulates way up into that stable layer, they could block or reflect back to space any incoming sunlight over an extended enough period of time to cause cooling. It is believed that the island eruption of Krakatoa is to blame for the Dark Ages that occurred from about 500 to 900 AD. The Little Ice Age, from about 1350 to 1850 AD, and to put this into historical perspective, remember that picture of George Washington crossing the icy Delaware? This has been attributed to multiple eruptions that occurred throughout the northern hemisphere, causing solar energy blockage. However, volcanic eruptions could also cause a warming effect. While volcanoes can spew a variety of greenhouse gases, those concentrations tend to be relatively small. However, sulfur is a very common element that gets ejected, and when that and other molecules finally settle into our waters, such as our oceans, the oceans become acidic. When the oceans acidify, it can kill off a significant amount of the ocean's plant life, and this plant life is a major sink of carbon dioxide. So without it, more carbon dioxide will remain in the atmosphere. Therefore, while volcanoes themselves tend not to emit a lot of carbon dioxide, the acidification of the oceans from the fallout of the volcanic particles can greatly reduce a major resource that normally removes carbon dioxide from our atmosphere, causing the atmospheric carbon dioxide to rise. So volcanoes certainly have a natural impact on our climate, and at times a rather large impact on our climate. To have a longer-term impact, though, there often needs to be multiple massive volcanic eruptions around the world. The other common natural influence on climate is sunspots. Sunspots are known to have about an 11-year cycle. However, you can see from this graph that the number of sunspots varies by quite a bit through each cycle. It is known that when there are more sunspots, temperatures tend to be greater, which is counterintuitive, I know. The global influence of sunspots tends to have a lesser impact on larger scaled climate change periods. Regardless, before I leave this plot, note that since the mid-1800s, the average number of sunspots, represented by the black curve, was gradually decreasing until the early 1900s, then started increasing at a faster rate up until about 1950, and then has been slowly decreasing ever since. So think about this pattern when we start looking at temperature trends since the late 1800s. It doesn't seem like sunspots have contributed greatly to the global climate change impacts that have been observed during the same time period. Before I go too much further, I want to show a few slides that explain how we can analyze and present climate data. There will be lots of time series graphs presented from here on out, and it might be good to think about some of these things. A lot of graphs that will be shown are time series graphs that illustrate a change over time for a particular variable, such as temperature. The change over time can be representing the absolute values of things like averages or as departures from some base period average. The base period is not always the same. It could be a 30-year period, a century, or some other period. Whatever base period is used, it does not impact the shape of the curve. The graph on top is the statewide average annual temperature for Indiana. The bottom graph has subtracted a 30-year average. In this case, the 30 years representing 1981 to 2010, from those actual values that we see above. Notice the shape of the two curves did not change, but a climatological perspective is better presented using the departure values from that bottom curve. When a zero line is highlighted, it is easier to see how much above or below some climatological reference point the individual years were. In climatology, a 30-year average period representing 3 consecutive decades is typically called a normal. So in upcoming slides, you may see a bit more of these departure maps and some that reference a normal period. In a previous webinar from this series, a question from the audience brought up how we apply a best fit line to data to show trends over time. The most common fit line is the linear trend line. This is most common for more recent historical data because we do not need to be worrying about longer-term natural oscillations. This method is also relatively easy to derive, and the conclusion drawn from the linear trend is that conditions have changed over time when comparing the value of the first point of the trend to the last point in the trend. The correlation of such a line isn't always the strongest. Note that in this case, the correlation is only 0.0726. The best possible correlation value we could get would be an even 1.0, but that would mean that all the data points were the same as the dashed trend line. Because the year-to-year data values are quite variable, the correlation is low. That does not mean that the linear trend line is inappropriate. It still shows the general trend of values over time. If the best fit is what we're after, then certainly other types of curved trend lines, such as the polynomial fit, may be more appropriate. In this example, a polynomial fit with an order of 5 is being used, and you can see how we can better identify cooler and warmer periods since 1895. The correlation is better than for the linear trend, that is 0.1825 is certainly bigger than 0.0726. However, it is much harder to see among the up and down waves if things are generally increasing or decreasing over time. As an analogy, using this technique allows us to see the waves in the ocean, but can't as easily see the overall rising or lowering of sea levels. The last thing I want to talk about is the period from which a trend line is drawn. Using the same time series, this linear trend line is accounting for that entire 125-year period of record. And this is totally okay. It's all about the question we're trying to ask. In this case, the question might be, how much has the annually average temperature changed since 1895 in Indiana? By looking at the start and end point, we can estimate that this is about 1 degree Fahrenheit. But what if we wanted to know about changing trends within that time period? I've highlighted periods where it looks like temperatures were increasing and then decreasing and then increasing again. By adding trend lines to the various periods, we can better see if trends have been changing more or less during some periods compared to others. Color-coded trend lines have been added to this time series. It is not difficult to see that temperatures were increasing in the early 1900s, then decreased in the mid-1900s, and then have returned to an increasing pattern since about the 1970s. This would tend to support the argument that climate has always been changing, and our current climate pattern isn't unique. Or another argument I've heard is that if carbon dioxide causes increasing temperatures and carbon dioxide has been steadily increasing since the late 1800s, then why was there a cooling period in the mid-1900s? So this might be a good time to talk about these arguments while looking at a plot like this. First, yes, temperature did increase in the early 1900s, but this wasn't attributed to an excessive number of sunspots nor volcanic eruptions. An increase of this rate was already looking greater than what was typical over the past 1,000 or more years. By the 1930s through World War II, industrial pollution had become so extreme that in addition to the greenhouse gases being released, there was abundant particulates being pumped into the atmosphere. While many particles can settle out of the atmosphere over time, the polluting sources such as factories kept pumping out more and more particles, and more factories were being built. So in essence, there were so many particulates being forced into our atmosphere that it was actually blocking sunlight from reaching the Earth's surface. Remember those massive volcanic eruptions that would cause extended cooling periods? The same thing was happening with these industrial particulate outputs, a clear example of how humans can modify our climate. We were realizing this impact enough to have Congress create the Clean Air Act of 1970. Part of this act was to greatly reduce the amount of particulate output from these polluting sources. It took nearly 10 years for industry and the atmosphere to respond to these new policies so that maximum sunlight was once again able to reach the Earth and stop the cooling trend due to pollution. This started the next phase of warming, and by now the expulsion of greenhouse gases have continued to increase, causing increasing concentration of molecules such as carbon dioxide in our atmosphere. So now compare the reddish-orange trend line for the early 1900s with the gold trend line for temperature since 1979. The yellow trend line is much steeper, indicating that the annual average temperature in Indiana is now increasing at a greater rate than when the temperature increased 100 years earlier. In the previous webinar of this series, greenhouse gases, and in particular carbon dioxide, was discussed. I want to briefly review this again in the context of temperature to help frame our more recent climate. Through the analysis of ice cores drilled from Antarctica, we are able to look at both carbon dioxide, shown here in red, and temperature, shown in blue, over the past several 100,000 years. Note how strongly these two parameters are correlated. Also note the pseudo-regular periodicity of these two variables. Each small tick mark along the bottom of this graph represents 10,000 years. So the far right of this graph, between the very last tick mark and the 0 point, which represents today, shows the carbon dioxide concentration and temperature between about 8,000 BC and present time. Think about what human history was during 8,000 BC. Now let's look at a similar graph that shows more clearly how the concentration of carbon dioxide, this time shown in blue, has been changing with respect to temperature that is shown in red. Because this graph is still representing a significant period of time, a vertical line is needed at the very end of the blue carbon dioxide curve to illustrate how today's concentration compares to the concentration over the past 400,000 years. Therefore, it is important to note that the concentration of carbon dioxide today is not only greater now than in a very, very long time, but the rate of the increase is unprecedented. This tells us that something else must be contributing to this rapid increase of carbon dioxide, since it has never been experienced in the natural cycles of Earth prior to the start of the industrial age. Another thing to note in this graph is the range of temperature at the end of the curve. First, it appears that temperature in recent years has not varied by a lot. Viewing those red squigglies to the far right with the axis labels on the far left that represent the temperature departures compared to the 1961 to 1990 time period. It looks as if the temperature has not varied by much more than a degree or two Fahrenheit, but note that the axis label is in Celsius. And even the clump of the recent red squigglies are below that red dashed zero departure line that's based on the 1961 to 1990 average. So let's zoom in a bit closer to that period and look at the global temperature departures for the past 1,000 years. Here, the reference period that the temperature departures that this curve is based on is the 1850 to 1900 period that is considered to be pre-industrial. The recent warming now becomes far more obvious. Keep in mind that the temperature departure values on the y-axis are in degrees Celsius, and for simplistic math, one can assume approximately 2 degrees Fahrenheit to 1 degree Celsius. Now we can start to see that temperature is indeed increasing, much like we know the concentrations of carbon dioxide are. Another interesting thing to note in this graph is that the data is representing globally average temperatures. Remember in an earlier graph when the medieval warm period, dark ages, and little ice age really stood out? Well, those graphs were displaying data from the northern hemisphere, where Europe, North America, and Asia are located. Those warm and cool periods are more noticeable in a regional temperature data graph and stood out so much more because they were driven by the impacts of volcanic eruptions, often in the northern hemisphere. Particulates that are forced into the upper atmosphere from a massive eruption tends to stay in one hemisphere and not interact globally. However, carbon dioxide is a bit more mobile, and the world ocean currents can help transport those greenhouse gases more globally. Okay, we've gone through our deep history of climate, talked about data and how we can present any sorts of trends. Now for the fun stuff. For the remainder of this talk, I'm going to step through a variety of graphs and maps to show how the climate of Indiana has been changing. So here we go. A lot of times, climate change, trends, and extremes are presented at an annual scale. However, trying to capture climate trends and extremes over an entire year can tend to mute out the finer details of the seasons that impact our lives throughout a year. Therefore, I'm going to present a few climate highlights by season to better illuminate some of the detail. When we think about each season and the potential climate impact, the topics change. For example, are our winters getting more or less snowy? Are tornadoes becoming more common in the spring? Are droughts becoming more common in the summer? Is the first fall frost occurring later than they did 10, 20, or even 30 years ago? This slide shows some of the topics and questions that affect us within each season. We don't have time to go into every one of these, but the rest of the presentation will pull a few of these out to show what, if any, trends have been occurring. Starting with winter, our winters seem to be getting less and less snowy. And if you're like me and enjoy a white winter, this is sad news. It can also be harder on our hydrologic systems, for if the ground is frozen, then precipitation that falls as rain rather than snow will be more likely to run off instead of gradually soak into the ground. If we look at the average 4-month snowfall totals from December through March for the past 4 years, we see that indeed seasonal snowfall totals have been less than the 1981 to 2010 normal period. Note the legend for each of these maps is slightly different, but the transition of colors from the above normal values to the below normal values are the same, where the yellow and oranges represent below normal snowfall amounts and the greens and blues represent above normal snowfall. There is year-to-year variability for sure, but there seems to be more below normal areas each year than above normal areas. To go back even further to the early 1940s, we see a bit more variability. This is for the station at the Indianapolis airport, and the averaged period is the entire record from 1943-44 winter through the 2018-19 winter. While the last 4 winters have been below average in terms of snowfall, the 3 years prior to that were above normal. In fact, the 2013-14 winter, often dubbed that polar vortex winter, was one of the top 3 snowiest for Indiana. It also appears that when a season is snowier than average, the range could be anywhere from an inch to over 30 inches above normal. However, when the season has been less snowy than average, the departure is never by more than 20 inches. But this could be because the average annual snowfall for this 4-month period is only about 25 inches. The winter season rainfall maps, and this includes the liquid melted from snowfall, are showing a wetter story. Aside from the 2016-17 winter, that 4-month precipitation total appears to have been above normal throughout much of the state the last 4 years. In some years, such as 2015-16, it was much wetter. If we look at the state as a whole back to 1895, though, the story looks a bit different. While there is clearly a lot of year-to-year variability of precipitation during these months, the statistical trend over this entire period indicates that precipitation is decreasing by only 1/100th of an inch per decade. You can see that in the top right. That's quite negligible. However, as mentioned earlier in this webinar, the period of applying a trend matters. By just visualizing the annual precipitation value since about 1995, one would think that it is a much more significant increasing trend. What about temperatures? Again, if we look back at the 125-year trend line, winter maximum temperatures, and this time we're just talking the 3-month December, January, February period, having only been increasing by 1/10 of a degree Fahrenheit per decade. However, if a trend line was drawn for data since 1977, that trend may be different. This linear trend may not seem all that significant. In fact, can we really say that an increase of just 1/10 of a degree Fahrenheit a decade is a big deal? Well, when we think of winter, though, the maximum temperature often isn't what we think about. The minimum temperature may be more relevant since this provides that experience of how cold the season was and whether or not we get snow or rain. Here, the 3-month averaged minimum temperature for Indiana is presented. For the entire period of record, there has been an increasing trend of 0.2 degrees Fahrenheit per decade. But over the whole period, this represents an increase of 2.5 degrees Fahrenheit, which is certainly enough to have an impact on whether the precipitation falls as rain or snow. And if it falls as snow, will it stay on the ground very long? Moving on to spring, let's look at the March, April, May precipitation totals for the state. There's a lot of variability from year to year, which may otherwise make it difficult to tell if there's been an increase or decrease in the seasonal amount since 1895. However, the blue trend line indicates that there's been 1/1500ths of an inch increase per decade, or almost 2 inches more rainfall on average in the spring today than there was 125 years ago. Another thing to notice in this graph is the change in variability. When we look at the earlier years in this period, from say 1895 through 1915, the spring precipitation totals seem to flip-flop every few years from a little over 2 inches above the 100-year mean to 3 to 4 inches below the mean. Then from about 1920 until the mid-1940s, look at how that interannual variability seemed to amplify. Suddenly, the swings were from 4 to 6 inches above normal to 4 to 6 inches below normal. But by mid-century, the interannual variability seemed to dampen a bit. And this seemed to continue until about the 1990s. So what this means is for about 5 to 6 decades, residents were getting used to a relatively predictable amount of precipitation from March through May. That predictability or consistency from year to year seems to be degrading now, once again, where we're seeing some wide swings from above or below normal precipitation from year to year. So while there is certainly an increasing linear trend that can be derived from the data, perhaps a more significant story that comes out of this is the increasing variability that we're seeing. This makes trying to assume what a typical spring will be like very challenging. Something that is certainly of interest to those in the agricultural community is the date of the last freeze in the spring. Melissa Whitholm had briefly mentioned this in her presentation when she talked about the expansion of the frost-free season. I wanted to explore this topic a little differently by considering the first date of a full 7-day period when the minimum temperature was greater than or equal to 35 degrees Fahrenheit. And it was, again, a 7-day period of this happening. And so why did I do this? Well, first, 35 degrees Fahrenheit is obviously a few degrees above freezing, but this would help account for any low-lying areas with microclimates that may still experience freezing temperatures, even though the weather station at the airport may not. Also, identifying the first full 7-day frost-free period will help minimize those intermittent events, and to also suggest a date when vegetation is likely to start coming out of dormancy. This does not mean that there were no frost or freeze dates after this 7-day warm period, because likely there was. However, plants emerging from dormancy don't realize this risk, and early emergence could lead to frost damage risk to our perennial crops such as fruit trees. So for this plot, the y-axis on the left represents dates, where higher up in the graph represents later in the season, and lower in the graph represents earlier. Each point represents the first date of the first 7-day warm period as recorded at the Indianapolis airport. There is certainly a lot of year-to-year variability, but the dashed trend line shows an overall trend for these warm periods occurring earlier. The average date over the period was March 30th, but the linear trend suggests the date could be moving earlier by as much as a week. But note, of the last 7 years, the most recent 7 years, 5 of them had the first 7-day warm period occur after the 76-year average. So again, variability is important to realize. Just because trends may indicate a general change in climate when considered over longer periods of time, the variability within that period of time can show contradictions to that trend that can make realizing the trend exists difficult. Wind. A question from the audience on a previous webinar asked about any known trends about winds, and in particular how it may be affecting coastal erosion. Well, I didn't look at coastal erosion, but I did explore what I'll call the number of windy days that have occurred at the Indianapolis airport. I apologize for the small font size on this graph. I grabbed it actually from my website, and on that website you can zoom in and be more interactive and so forth. But to explain what's going on here, I counted the number of days where the average wind speed for any hour within that day was greater than 20 miles per hour. Again, this was an arbitrary speed, but I knew from experience that when wind speed averaged around 20 miles per hour or more, it was certainly noticeable. The top row is the number of daily counts by year for March. The middle row is the number of daily counts per year for April, and the bottom graph is the number of daily counts by year for May. The period starts in 1970 and runs through 2019. The linear trend line is shown for each graph, and while I don't show actual trend line values, it is interesting to note that the trend line for March is pretty much flat, meaning there is no appreciable increasing or decreasing trend in the number of windy days for March. However, check out April's trend line. There is a clear increasing trend, and estimating the value at the start of the trend line in 1970 to the end of the trend line in 2019, it looks like the number of windy days has increased from about 9 days to around 13 days. And remember, April just has 30 days. May also shows an increasing trend in the number of windy days, but that increase does not appear to be by as much as was found for April. Okay, if we're going to talk about windy days and we're focusing on Indiana, then we've got to talk about tornadoes. However, tornado data can be highly questionable, particularly in the early part of the data record, which in this case starts in 1953. Prior to the installation of Doppler radars in the early 1990s, tornadoes were often determined by human observations and possibly the presence of a hook echo within the pre-Doppler weather radar images. So, like the whole tree falling in a forest with no one around, if a tornado touched down and there was no one to see it, or nothing in its path to be damaged, did it ever exist? So, Regardless, we can still look at the annual number of tornadoes in Indiana and see if there's any possible interesting trends. Again, I apologize for how small the font is on this graph, so let me explain what's going on. Each group of colored bars represents a separate month, starting with January to the far left, colored with the blue bars, and progressing all the way to December on the far right. In the middle, the mustard, orange, then reddish-orange color groupings represent May, June, and July. The year range within each color grouping is from 1953 to 2019. And the black line running through each grouping is the trend line for that month. Upon first glance, the most active months seem to be March, April, May, and June, and this is relatively common knowledge for residents in Indiana. The trend line throughout most of these months indicate that the number of tornadoes is increasing, but remember, the reporting methods have changed over the years, so it's difficult to say how physically realistic this is. However, May's increasing trend line, where May is that mustard green color grouping, does seem to indicate quite a bit more tornadoes reported in recent years. There are two other months that stand out and worth noting, October and November. Both of these months show an increasing trend in tornadoes, and some of the recent years' counts for those months are starting to rival those of the more popular April through June tornado season months. In other words, this suggests that Indiana is developing now two separate tornado seasons, a spring and a fall season. This could certainly be due to climate change and something researchers will keep an eye on over the next few years, if not decades. Moving on to summer, a common concern is another big drought year. A rather popular indicator of drought intensity is the Palmer Drought Severity Index, or PDSI, which is an index based upon precipitation, temperature, and soil moisture. This chart tracks what the August, because they're monthly indices, August PDSI was since 1895 for Indiana. When the PDSI is positive, represented by green bars in this graph, this implies a wet period. And when it is negative, represented as orange bars in the graph, this implies a dry or drought period. The most notable drought periods in Indiana were in the 1930s, less so in the 1950s, and then the 1988 drought, all of which show up nicely in this graph. The linear trend of this drought index indicates that increasing trend in PDSI is occurring. This is hopefully good news for things like agriculture and water supply in Indiana. However, this index likely fails to capture how evenly the precipitation has fallen over time, and what does fall may be so intense as to run off before being able to adequately soak into the ground and groundwater supply systems. And like many other climate parameters, this particular one is also as susceptible to variability. So another drought year in our future is not unlikely. And we have quite a run going so far for positive PDSI August. We might soon be due for another drought. Sunshine is another parameter that people have been talking about recently. The data for this is not as prevalent as it is for temperature and precipitation, but we do have a weather station down in Bedford, Indiana, that has been recording incoming solar radiation data since about 2008. This chart is very similar to the one I recently showed for the monthly tornadoes. Only June, July, and August are highlighted here, but you can faintly see the information for the other months if you're interested. I think a key takeaway from this graph is that nearly every month, with the exception of September and December, is showing a decreasing trend in incoming solar radiation. What could be causing this? Well, with increasing atmospheric temperatures, there is an increased capacity for water vapor and therefore cloud formation. Clouds tend to block or reflect back to space any incoming solar radiation. So the fact that we have less sunlight coming in could be attributed to more water vapor and therefore clouds developing due to the increasing temperatures near the Earth's surface. You might ask, though, that if there is less sunlight coming in, then wouldn't that cool our temperatures and help reverse global warming? Good question. But remember that water vapor is actually our most abundant greenhouse gas. It's natural in its existence, so the more vapor in the atmosphere, the more absorption and re-emittance of the Earth's heat is occurring. The warmer the atmosphere, the more vapor the atmosphere can hold before it must condense into cloud droplets. This is certainly something to think about and consider what sort of impacts all of this may have over time. For growers, the accumulated growing degree days each year is an indicator for varying stages of plant growth and when to harvest. There are a variety of ways to derive the number of growing degree day units in a day, but most involve some form of finding the daily average temperature and subtracting some base temperature value. So if the base temperature is 50 degrees Fahrenheit and the average daily temperature was 70 degrees Fahrenheit, then the difference would be 20 units. This plot shows the annual accumulated growing degree day units at the Indianapolis airport since 1943. As with the other variables I've shown, there is certainly quite a bit of interannual variability, but the overall trend is clearly increasing. Simply looking at the estimated trendline value in 1943 compared to where the line is in 2019, the change is about 450 units. This could certainly be a positive impact from climate change if it means the possibility of additional crops to try in Indiana. Of course, this all comes with this risk of variability. Notice the low number of accumulated growing degree days as recent as 2014. That interannual variability can sometimes be just as maddening to adapt to as any gradual change in the overall climate. Which brings us to the last graph I wanted to show you. In 2019, the growing season was off to a very late start due to cooler spring temperatures and a very wet spring planting season. This late planting led many to worry about the possibility of crops even making it to harvest before the first fall freeze. This led to the question of whether or not our first hard freeze, defined as 28 degrees Fahrenheit, was occurring later and later in the year due to climate change. You saw a similar plot to this earlier in the presentation when looking at the dates each year when there were 7 consecutive non-frost days in the spring. This one has the same layout where the dates are along the left-hand y-axis and range from the early date of October 9th down at the bottom to the latest date of November 28th at the top of the graph. The years run from 1981 through 2019. This data is from the Climate Division representing the middle of the state of Indiana. The average date for the first hard freeze over this time period is November 3rd. However, the dashed red trend line does imply that the date is getting increasingly later over the years. Eyeballing the trend line at the far right with the labels along the left side axis suggests that climatologically speaking, the first hard frost should now be occurring closer to November 8th or 10th. But there goes that interannual variability again. Last year's first hard frost was slightly earlier than average and contradicted the trend that was the first hard freeze is now more likely to occur later in the year. So in summary, there are indications from our observational data over the past 100 or so years that our climate is changing. There are noticeable trends in temperature, precipitation, dates of first and last hard freezes, drought or non-drought periods, tornadoes, and much more. Some of these trends can and will cause negative impacts unless we try to adapt, but many of these trends can be viewed positively in such a way that we could take advantage of them. Regardless, remember that trends don't always tell the whole story. Just because the temperatures are rising, precipitation patterns are changing, and growing season attributions may appear to be working to our benefit, year-to-year variability still matters. We seem to be breaking new records all the time, and not just from warm temperatures. Remember just recently that Mother's Day weekend cold event just a few weeks ago that brought freezing temperatures across much of Indiana? It's these wide swings of extreme conditions that we need to be preparing for and aware of as part of our more slowly progressing trend toward a different climate across our state. Please join us for our next webinar in this series called Climate Change Mythbusters. Here we will run through a variety of statements heard over the years that challenge the idea that climate change is occurring, the causes of climate change, and other relevant myths. Dr. Jeff Dukes We'll be leading this webinar that will be held this coming Thursday, June 18th at 3 p.m. Eastern Time, 2 p.m. Central Time. Be sure to email Jeff, Hans, or Melissa if there are any myths or common challenging arguments that you would like to be addressed. Here's our digital business card. I'll leave this up for a few minutes in case you want to take a screenshot or a picture of it for your future reference. This 6-part webinar series has been a collaborative effort from Jeff Dukes and Melissa Widholm of the Purdue Climate Change Research Center, myself from the Indiana State Climate Office, and Hans Schmitz and Austin Pearson from Purdue Extension. Please feel free to contact any one of us if you have any more comments or suggestions. Thank you so much for your time, and I'll now pass it back to Melissa.
So we have one question that has come in. It moves on me when I'm trying to read them, and more questions come in. Trends at one location versus graphical area trends, perhaps variability linked to broadening on graphical trends. So, Beth, I think what Larry is asking is how the spatial area that's included in your data sets could adjust or affect the trend that is seen, that you that you are seeing. Do you have any comments on that?
I don't know if I understand exactly yet.
Yeah, so it sounds like he's saying, if you're looking at a point versus if you're looking at a larger area, are you going to be seeing different trends? Is that what's going on in a lot of these instances?
In terms of absolute values, you could, but I know there's been studies, for example, that have compared the general trend of an urban location station and a rural location station. And while, like I said, the absolute values may differ, what we have found is that overall trend is still very similar to each other. And the variability, like I kept talking about that interannual variability, that will still be the same. So that, I always did the Indianapolis airport because it was a very central location. But if I would have grabbed, 5 other locations across the state, I am fully confident that the trends would have still been there and we still would have seen similar variability from year to year.
So we have another question from Leslie. And she's asking, why is it that we use a 1981 to 2010 normal? Doesn't that include some global warming data? I know you touched a little bit on, we use different periods for normal depending on, what our application might be, or just some characteristics of the data set. Maybe you could talk a little bit about climatological norms versus maybe how a general application might want a different time period or something like that. Take it away.
Right. So every 10 years, the climate community updates their normals. So you would think that at the end of this year, we should have a new normal base period from 1991 to 2020. We like that 30-year period because we feel like that represents a lot of the interannual noise, if you will. But in all reality, I could have used the 1971 to 2000 period for it. I think using the most recent 30-year normal that we have, not necessarily our most recent 30 years, but the most recent 30-year normal, is because that is what we are most familiar with. I mean, I could go and grab a 30-year period from the 1700s, but I feel like that would confuse people. They'd be like, well, wait a minute, that was totally a different time. So we try and grab the most recent normal because that's what people can physically remember. But again, the shape of the curve would not change.
We have another question that came in from Melinda, and her question was, I think one that I can just briefly answer. It asks, are you looking at secondary and tertiary impacts, invasive species, diseases, etc.? That's certainly outside of the scope of what Beth was talking about today, but definitely something that people in the climate change community are very much invested in looking at. There's a lot of observations, trying to understand how invasive species, diseases, et cetera, are responding to the changes, right? Because this is an interconnected climate system that we're talking about. And so when you have changes to the atmosphere, changes to ocean circulations, changes to land cover, everything living in that system responds. So while it was outside of the scope today, which is why we didn't talk about it, there are folks at Purdue and other places in Indiana and around the world looking at those types of questions. And if you go to indianaclimate.org, where you'll find all of the reports that we've released for the Indiana Climate Change Impacts Assessment, you'll also see a lot of those secondary and tertiary impacts addressed. Do you have anything else to add on that, Beth? Since you're the speaker, sorry, I just kind of...
No, it's just when I think of animals, I think back to those pack rat mittens that I talked about early on.
I had never seen that photo. It was interesting and disturbing at the same time.
Right? Yeah.
So we had another question come in from Sylvia asking if we can talk a little bit about how land use change is perhaps having an influence on any of the climate variables that you presented, particularly precipitation, so changes in deforestation or agriculture or urbanization, and how that may or may not play a role.
Yes. So we do know that there is an urban impact. So the more asphalt and concrete and so forth will heat up those local temperatures compared to temperatures being observed outside of that. We also know that because of that increased heat source around these metropolitan areas, will cause enough uplift in the air passing over that it could induce downstream precipitation. So we are seeing in some case studies, whether it be Phoenix or St. Louis, that we do see more downstream precipitation and we do see more increased temperatures around the metropolitan areas. But that being said, while there's an increase in the absolute numbers, we're not seeing that the trend is really any different or the variability is any different. So land use is going to impact the absolute values in terms of, gosh, it seems wet, gosh, it seems warm. But if we looked at the long-term trend, we wouldn't see any sort of contradiction.
We have another question that came in from Karina, and this might be a good question for Jeff, and perhaps it's something also to talk about in subsequent presentations. So Jeff, if you're around and you would, he's answering somebody else's. Okay, so the question I had in mind, Jeff, I appreciate you typing into the chat box. No, that's fantastic, and it helps us get a record of what's talked about, so people who are taking notes. So Karina's question had to do with the longer term, the geologic changes in CO2 and temperature, and how it looked like she's seen this used by climate change deniers because temperature changes before CO2 level. Can you explain this?
Yeah, it's a back and forth dance. You get CO2, when CO2 goes up, it causes warming, and the warming can cause sort of additional feedbacks to kick in. And when CO2 goes down, that ends up causing cooling. And so there are, I guess I should say it's the feedbacks between the two that end up sort of amplifying each other and causing that dance. But the critical thing is that the CO2 is long lived in the atmosphere, and while it causes a lot of subsequent positive feedbacks, it's essentially the driving knob in this process. And I'll try to address this in more depth actually on Thursday, because I think that's a great sort of mythbuster question, and I can provide a more illustrated answer at that point. But it is a complicated dance. They do influence each other, and in those cycles that you're seeing, really that were presented earlier today, the driving factor is the orbital cycles, the Milankovitch cycles that Dr. Hall was presenting, the differences in precession and eccentricity. et cetera, that are changing where light is coming in, changing the seasons on the planet, and leading to those changes. So anyway, more on Thursday, but it's a reasonable observation, but it's not a contradiction of climate change being caused by CO2.
Thank you, Jeff. See, I knew I handed it off to the right person, and that it could certainly be something to include on Thursday. And with that, I'll do a shameless plug to remind everyone, if you're not registered for Thursday, please go ahead to the website, go to purdue.edu/climate. Right there from the homepage, you will find a link to the registration page where you can find materials and resources from past webinars and sign up for future webinars. It looks like we have one more question for you, Beth, and that is a question from Shibai asking, do we have data on temperature trends and changes in the amount of cloud formation?
Wow, that's a good one. That's one of those obscure parameters that I don't have in my back pocket, but I know that climate scientists that work more with satellite data, remotely sensed data, I know that they are doing measurements like that, because they can take the photographs that the satellites send back, and they can then measure how much of that image is bright white of the cold, tall clouds versus more of a gray of maybe the middle stratus clouds and so forth. So I don't have that data. If you're interested in it, please feel free to email me, and I'll do my best to track down who has it and what sort of social life do they have if they're looking at that. I'm just kidding.
I was just thinking I would love to see those data, so perhaps I have very little social life, which serves me well in a pandemic.
Yes.
All right. I think this will be our final question. Just looking at our time, we are just 1 minute off from the top of the hour, and while we say these last approximately 1 hour, it's always great to be respectful of everyone's time and wrap it up in a timely fashion. So Leslie asks, looking at 100-year historical data is interesting, but those of us who are paying attention seem to have observed significant changes in the last 20 years. How would your presentation change if you just focused on recent data? And I think you spoke a little bit about this, Beth, how the period of time matters. And that's not to say it's right or wrong when you look at a different time period. It's really a matter of how vulnerable does that make you based on what you've built your society around, and also what your application and purpose might be. So additional final thoughts on that, how your presentation might change if you focused only on the recent data?
Yeah, I think I've heard people debate both sides of it, and it's an entertaining debate, because if you only look at a short period of time, say the last 10, 20, 30 years, you're going to have critics say, well, you've just grabbed one snapshot of what is a naturally changing, oscillating environment. And so you hid much of the story by not going back further in time. But yet, if you go back further in time and show trends over that whole period, then you have critics saying, but you've just muted the intensity of change that we've seen in the last 30 to 40 years. So I feel like it's, I can't win the argument in terms of how the best way to present it, but that's why I really did want to dedicate some time on that 1 or 2 slides saying, yes, the period of your trend analysis does matter. So when you're looking at any time series graph, even if there's a trend line for one period, use your eyes, start to analyze different periods that maybe the trend line isn't there, but is telling a story that will answer the questions you're asking. Because there's no right or wrong way. It depends on the question that's trying to be asked.
That's right. And it's really, that's the beauty of climate data, is that you can see so much more than just an average or just a trend. And, we can tell a much more complete story when we look at the data from different angles through different time periods. And when we start to see multiple lines of evidence all pointing to that same conclusion, that gives us a lot of confidence that we have an understanding of how the system is working and what we need to be thinking about in terms of how we adapt to it and interact with it so that we can try to make the most of what's happening now and preserve a better climate for the future by taking actions today. So with that shameless plug for session 6, if you want to know more about what we can do, again, remember to please go to the website, sign up for our future sessions, check out the past recordings. If you have questions for us after this webinar, and some of these that have been coming in at the end, we can certainly try to answer those in upcoming sessions as well, or reach out to us by email.